Earlier this week, I went to one of my analysis instructor's seminars, and someone in the classroom had asked him to cover Runge's theorem, which is a famous theorem from complex analysis. It depends though, there may be more than one Runge's theorem, but the one that we learn in complex analysis is kind of complicated, more or less. It depends on what you're doing with it. But anyway, so this student asked my instructor, or our instructor, to cover Runge's theorem and how it relates to Midig-Leffler theorem, I think it is. The names kind of escape me at the moment. I need to review my complex analysis. I tend to study real more than complex, if you couldn't tell. But we covered Runge's theorem, or Runge's. I go back and forth between the two. So I thought I would show you this handout that he gave us, because he doesn't normally give us handouts. So when he does, it's kind of interesting to see his handiwork. And this is his handwriting, by the way. But there's two versions of Runge's theorem's proof in this packet. There's my instructor's and then the other complex analysis instructor's version of the proof. So I'm just going to go through this somewhat thoroughly, but not too much. I don't want to spend too much time on it because this proof takes a while to get through. But I thought this packet was interesting, so I figured I'd share it here. So what does Runge's theorem say? So the statement says that if you have a compact set in the complex plane, which here he calls K, provided that it has a connected complement, which means that you can, given any point in the complement, or given any 2 points in the complement, I believe you're able to draw a line segment. It doesn't have to be straight or anything, such that the entire line that you draw, or contour if you want to call it that, is contained in the complement. So no donut shapes. If f is a function analytic in some open set omega that contains k, then for any epsilon greater than 0, we can find a polynomial p such that the difference between f and p is within epsilon on the compact set. So in other words, you can approximate an analytic function arbitrarily close with a polynomial on a compact set that you're given. That's more or less what Runge's theorem is about. The proof of Runge's theorem is kind of complicated. So there's a couple different versions of the proof in here, and it's divided up into 3 steps. So the first step is rational function approximation, which means that we're going to approximate it with a rational function first, and then get a polynomial from that rational function. Okay, so what's the first step here? For each z in the in the compact set, we can find a radius such that the disk of 2 times that radius. That sounds kind of strange. It's not really a radius, but you create a disk and then you double its radius to make a new disk, such that it is contained in omega. But does it contain k? It doesn't really say. Choose a finite subcover of k given by the following. So each of these disks, so just as a note on his notation, he puts the radius inside, which is r sub z sub j, meaning that the radius is dependent upon this point zj, and so the center of the circle is zj. For me, I like to interchange these two. I like putting the radius down here and then the center inside the parenthesis, but he likes to do the opposite. So because the set's compact, you can find a finite subcover using these radii centered at zj. Yep, that makes sense. Then omega complement, which is represented as the union of these disks. Okay, so that's just notation. It is an open set containing k whose boundary omega k, or omega boundary of omega prime consists of finitely many arcs. By the Cauchy formula, we have the following. So you do need to use some prior knowledge, like Cauchy's formula, in order to solve this. So before I continue with this proof, I should mention that he doesn't really have this proof on the ready when he presents it to us in class. What he does is that he explains stuff with a picture. So he's using a picture to guide his his proof. So his, hold on, where's the pictures at? Okay, so here's his pictures. So here's what's going on here. This region here is my K that's shaded in. And then omega is this open set that contains K. And what he's done here is that he's picked ZJs such that the disks of those radii centered at those ZJs. And it looks like those ZJs are on the boundary, I think. Yeah, I think he did say it was on the... Well, he said it was on the boundary... No, I'm sorry. We were talking about the boundary of omega. Let me see. What exactly has he done here? Because he has it labeled the ZJs. But anyway, when he mentions the arcs, these are the arcs of the disks that he's talking about. The go around K. And then here's how he's going to use Cauchy's formula later on. So it says here if z is in K, then fz is equal to that integral from Cauchy's formula. And it appears that we can decompose the integral. So it looks like he's called it omega tilde here, but in the previous, on the first page, he called it omega prime. But all he's done here is he's split up the integral over arcs. And he's named the arcs gamma j. And this is approximately equal to 1 over 2 pi I sum j. Wait, how is this different? Oh, he's got zeta j in the denominator instead of zeta. Okay, so the big question here is what are these zeta j's? I mean, zeta j here is a point along the arc. But I need to figure out if it's like a pole or something. Okay, let's continue the proof. Since K and omega, or the boundary of omega prime, are disjoint compact sets, the distance between the two can be represented as the minimum of the absolute value of z minus zeta, where z is in K and zeta is on the boundary of omega. This distance is positive. Okay, big deal. Let delta be positive and be chosen later. Split the boundary of omega prime into pieces gamma j. Okay, we all saw this from the picture. And let zeta j be the middle point of each gamma j. Then for zeta on gamma j, we have the following. Okay, so that's what he's chosen zeta j's to be. Okay, so the difference between these two, is zeta just a point on the boundary? I don't know. Okay, it looks like it is. It's a point on the boundary. So we're measuring the difference between these two. So what can we say now? Okay, so he's established like denominators. He's pulled out f zeta in modulus. Everything here is good. And now he's going to get an upper bound. So he's replaced absolute value or modulus f zeta with the maximum, so the largest possible value he can pull out. And then the top, zeta minus zeta j, is bounded above by delta, I guess. Because why? The length is less than or equal to delta each. And let zeta j be the middle point. Split the boundary into pieces of length at most delta. Okay, so I guess that makes sense because the distance between these two can be at most delta. All right, I'm with them now. And then the bottom, he's replacing with d squared because that's how he defined d upstairs. Okay, so what does this tell us? It says that fz minus the sum, so that's the decomposition he created, is bounded above by 1 over 2 pi, so he pulls out the 1 over 2 pi. It looks to me that he's established like denominators again. Okay, he's lost me. Because he has f zeta here, f zeta over zeta minus z here. I don't see how he's able to put the fz inside the integral. Okay, I guess I'll see it later, maybe. But he's establishing a like bound. So essentially what he's saying is that he can make these two arbitrarily close to one another. So the 1 over 2 pi goes here. He has this substitution that he brings downstairs here. So we have maximum of f, the length of the boundary, which makes sense if we're integrating over the boundary. And then we multiply by delta. And then where does delta come from? Delta is this guy here from where he creates like denominators. Okay, I'm with him now. And this tends to 0 as delta tends to 0 because d is a fixed length. We're multiplying some constant by delta, and then we can let delta go to 0. So what does this tell me? It says that f can be approximated on k by a rational function. And then he gives the rational function there. With poles zeta j not in k with arbitrary uniform precision. Or precision. I can speak English. Precision. Okay. I believe that's step 1. So what's step 2? Moving poles to a single point. So this is a necessary step in between getting the rational function and getting the polynomial. Okay, so zeta is not an element of k. Let r sub 0 be this some rational function, I should say, with the pole zeta sub 0 not in the compact set k. Then there exists a rational function with a single pole zeta such that the difference between r0 and r is uniformly as small as we want on k. Okay, so why is he able to make these two really close? I think that's probably the thing we just proved, right? Oh, I hate this theorem. I hate this theorem in part because there was a problem on my qual last year that used this theorem in it. And surprise, surprise, I did not get the question right. Okay, so the complement of k is a connected open set. There is a broken line gamma that begins at zeta 0 and ends at zeta. Choose delta between 0 and 1/10 the distance between gamma and k. Okay, fine. I don't really see why. I know this is a necessary step. I just don't see why we need to do it at the moment. Mark some sequence of points on gamma so that the distance between any two consecutive points is less than delta. So notice that z, the distance between z and zeta 1 is at least 2 times delta. Okay, I don't even know what z is now. Where is z? I think z is in k, perhaps. Doesn't really say on this page. What's z? I guess it's the same as this z that's in k. I mean, I don't really have any reason to believe otherwise. So how do we push the poles? So we have 1 over zeta minus z, okay, and then he adds a 0 in the denominator, where he adds zeta 1 and subtracts zeta 1. And then he pulls out a 1 over zeta 1 minus z. It might be hard to see if you're not familiar with this trick, but he pulls this out, which leaves a 1 here, I think. And then this, we get a zeta 1 minus zeta 0 over zeta 1 minus z. And then you'll have a fraction that can be rewritten as a geometric series, which is given here. So I have 1 over zeta 1 minus z times the geometric series. And because the fraction, this fraction is at most 1/2 of 1 over delta, because of this relation here. And we know the fraction that's inside is at most 1/2 because the top is 1, or that. The difference between the top is delta, given here, and the bottom is at least 2 delta here. We get 1/2 here. So the geometric series converges. And it gives us an error at most. Oh, so he's truncating. Okay. Yeah, he writes truncate here. All right. I need to read the thing. Truncating the series at the kth term, we make an error at most this. So so what he's done here is I think he's trying to create his polynomial. And so for a polynomial, you need to stop at some point. And here he's chosen at the kth term, so we get uniform approximation on k. All right, let's wrap this up. I think he's almost done. So 1 over zeta 0 minus z can be approximated uniformly on k with arbitrary precision. I can't say that word apparently. By some rational function r1 tilde, with the only pole at zeta 1, hence so can any power given here. So we conclude that for any epsilon sub 1 positive, we can find a rational function given here, such that the difference between r1 and r0 is at most epsilon sub 1 on k. And then you repeat the same argument for the different terms of the sequence, choosing sufficient epsilon so that their sum is less than epsilon. We conclude that there is a sequence of rational functions r sub l with a single pole zeta l such that the difference between the two is less than epsilon sub l plus 1. Okay, and then he adds all those rational functions together, or the difference between the two. So let's look at the picture for this, because I'm struggling to understand what he's saying. So here is our picture of k. He chooses, so all these points are zeta sub j's along this path gamma, and we've chosen them in such a way that the distance between them is at least 2 delta. And the distance between gamma and k, so gamma is the name of the line, and our compact set is equal to 10 times delta. Here's another thing, why didn't his 10 delta come into play? I'm sure it did, I just missed it. And there's the equation that he sets up at error at most 1 over 10 delta times 2 to the negative k. Imagine being good at mathematics where you can just write this up, because I can't. Step 3, the creme de la creme. From a rational function to a polynomial, by the result of the previous step, we can find a rational function r close to f with a single pole zeta that can be chosen anywhere outside of k. So we choose this zeta such that the modulus of zeta is at least 2 times the maximum of the modulus of z, where z is an element of k. So he wants it sufficiently far away. And what's he going to do? 1 over zeta minus z can be rewritten as the geometric series given here, and the fraction inside is at most 1/2. Arguing as previous step, we see that r and therefore f can be approximated by a polynomial on k uniformly with arbitrary precision. The end, smiley face. Okay, so this theorem takes a long time to prove. Holy crap, that scared me. I think that was a trash bag, to be honest. Anyway, so this problem, or not problem, but this theorem is kind of involved in the Stein-Shikarchi book on complex analysis, which I read before I took the test. It busts up the theorem into like 3 lemmas first before they prove it. It takes a while to prove. And the proof they give in the book is different from the one that my instructor gives here. But the proof that I showed you here, if they asked you to prove this theorem on a test, this is what you would need to write in order to get full credit. And then he writes an abridged version, which I'm not going to go through. But this abridged version, he says, is worth like most of the points on the test, without getting full credit. So you can see it's about 2 pages. And this time he ends with a boxed smiley face instead of a full one. Okay, so what about the last picture? I didn't actually go through it. So here's K, here's the origin. He wants a boundary at most 1/2 absolute value zeta. So he chooses zeta sufficiently far away so that this fraction is at most 2 to the negative k. Because he truncates, right? To get his polynomial. Okay, so that was my instructor's proof, everything considered. And then this next part, which I'm not going to go through, but this is the other instructor for complex analysis. He asked him to provide his own proof of Runge's theorem and write up a proof of it. And he did that for him and gave him his copy here. So this is his proof of it. And for the most part, it's pretty similar, but there's some fundamental differences. So for one, he splits it up to, well, he calls it Runge's approximation theorem, but he also has Runge's little theorem, which is like what really the theorem was about, or at least what my instructor had written. And then he prepares for the proof, so he needs Cauchy's formula, so he matches him there. You can pause the video and read this if you want. But he makes a statement towards the end. Okay, so he's got a couple lemmas here. Maybe one day I'll be able to do this from memory. But this statement here we remember from the previous proof. So instead of using disks and arcs on the circle of those disks, he uses a grid. Essentially, he creates a, square grid that he overlays on top of his compact set K, and he integrates along the boundary, so he gets line segments. The instructor for this complex analysis course is very geometric with his arguments as opposed to, I guess, analytic. But it's all the same. And so now, proof of Runge's approximation theorem, use the first 2 lemmas, and then he's done. Pole shifting theorem, so that's him moving the poles around wherever he wants. And then we get to proof of pole shifting theorem. What? I thought we already did that. But this line was the line that caused a lot of confusion for people. So I guess I'll read this statement here. For omega in the complement of our compact set K, let L sub omega denote the set of all functions analytic on K that can be approximated uniformly on K by polynomials of the form 1 over z minus omega. Notice that 1 over z minus s is in LC. So what's C? Oh, so C would just be this point here, but again, what is C in the grand scheme of things? C, I believe, are points along that contour gamma that we had from the previous proof. But he's saying here that this is in LC, and 1 over z minus c is in LB, and by transitivity we have 1 over z minus s in LB. He kind of sweeps these details under the rug, and unless you actually read through his proof and paused and read through it, it doesn't really mean much. But his statement is true, and the proof does end up working. If I had to take a guess, he probably got this proof out of the Alfer's complex analysis book, because that seems to be his favorite text, or at least for complex analysis. My instructor that taught this class did not use a textbook. He did everything from notes. But anyway, that's Runge's theorem. It's definitely not one of my favorite theorems from complex analysis. I think I mentioned in a previous video that the Cauchy-Goursat theorem was my favorite, and it still is. But when I see theorems like this, it makes me think about like how not good at math I am and how much of a long way I have to go before I can, you know, walk into a room and say, yeah, I can do math. I used to say that, but not anymore. Anyway, this video's gone on long enough. I hope you enjoyed it.